This episode is called Airplane Air Quality and Air Filtration by David Space, a former Boeing engineer who spoke at the National Air Filtration Association's technical seminar in Louisville, Kentucky in April of 2022. Enjoy!
You're listening to the Talking Air Filtration podcast, where you get to know the people that make air filtration possible and help us all breathe easier. Because clean air matters.
We'll get insights from air filtration professionals and learn how they became successful in their careers. Along the way, we will discuss best practices, guidelines, trends, and challenges in air filtration in a variety of applications. We hope HVAC, air filtration, and indoor air quality pros, including business development, engineering, building owners, and facilities management, will enjoy the insights our guests will bring to this podcast.
Good morning. Appreciate the opportunity to talk to you today. So I'm going to talk about the airplane cabin environment. We'll first start about talking about the environment that the airplane operates in. It's a very, very harsh environment. And we'll talk about the environmental control systems. How do we design it to be able to operate in such an environment? We'll talk about the kind of the history of air filtration. We'll also have a good section on spread of disease. What does the latest research show for aircraft and spread of disease? And then we'll talk also about air purification technologies. And I think that's going to lead to a next generation of environmental control systems. And also as we move to new regulations. So the outline, I'll talk about the operating environment, how the airplane environmental control systems work, advancements in filtration, latest in spread of disease, and then the air purification performance regulations. So airplane operating environment is really quite harsh. Very dry, very cold, minus 45 to minus 85 degrees Fahrenheit is typical operating. Minus 70 is a standard day. Very low in pressure. Mount Everest is 29,000 feet. Airplanes operate typically above that. And depending on the time of the year or location that the airplane flies, you can also have high ozone levels. So to operate in such an environment, we do need to have an environmental control system that's capable of providing a healthy and comfortable environment. Our cabin pressure is typically 6,000 to 7,000 feet, especially for oxygen content. It controls for ventilation. Thermal is, very important with such an environment. And then there's other functions that the environmental control system operates for: wing anti-ice, engine anti-ice, cargo heat, and such. So I was going to just briefly walk through how the ECS system works. So you have out here very cold, very dry, very low pressure air. Once it goes through the compressors of the engine upstream of where the fuel's added, the air is now brought up in temperature to about 650 degrees Fahrenheit, 45 psi. It goes down into air conditioning packs. Typically in flight, because of the high density of people and the in-flight entertainment, it's actually quite often in a cooling mode. And so quite often our air coming from our packs is 60, 65 degrees. It goes to a mixing chamber where it's mixed in with recirculated air here. And so the combination of air in the mixing chamber is about half outside air, half filtered recirc air. Goes up ducts. We don't have all the ducts in the schematic here. I think this 6-7 has 3 on each side, but it goes to the overhead air distribution system, which runs the entire length of the airplane. As air continuously flows in, it continuously leaves the airplane through outflow valves, often in the aft part of the airplane. Some airplanes have them in the forward part of the airplane as well. If we look at the cabin air distribution, we provide air from the top. We exhaust at the bottom. We have a very high airflow, typically 20 to 30 air changes an hour. The air distribution runs the entire length of the airplane. The exhaust is kind of where the sidewall meets the floor. And again, that runs the entire length of the airplane. Filtration on aircraft. So I was going to talk just a little bit about the advancement, a little bit of the history. Our first aircraft that had recirc system was the Stratoliner back in 1945. Following that airplane, we didn't have recirculation for 1950s, 1960s, 1970s. But there was research done by NASA, McDonnell Douglas, and American Airlines that showed that you could recirc some of the air, highly filter that air, and you could provide good air quality. And so that led into filtration systems on aircraft. So in the 1980s, the Boeing came out with the 757, 767, had recirc systems, 50-50 system, 50% outside, 50% recirc, two-piece filters, pre-filter, coarse, HEPA type, about 94, 95% efficient. We also came out with carbon filters, but we didn't know how to quantify the benefits. Airbus came out with two-piece filters. Working with the suppliers, we were able to get rid of the pre-filter, go to a multi-V design on the HEPA type filter. Our limiting factor for life on airplanes is typically lint. We have people come on the airplane, come off the airplane very frequently. There's a lot of lint buildup. By going to multi-V design, we're able to get about 5 times more face area. In the end, we're able to increase life, cut weight for that filter design. In the 93 timeframe, working with the filter suppliers, we're able to get it up to 99.9. And then just before 2000, we're able to get up to true HEPA filters. And part of it is they had to improve their internal processes. It's the same media as used in hospitals, but our airflow, the velocity through the media is typically higher on an airplane. And so they had to really work on improving their processes so that the entire lot set had an efficiency above 99.97 at the 0.3 microns. First generation air purification technology was evaluated. We went to the Technical University of Denmark. It's a leading institute that does air quality research. One of the top. We were there for 4 years. We tested ventilation, contaminants, humidity, particulates, and we showed a benefit on air purification. And then in 2015, we did about 7 years of research at Lawrence Berkeley National Labs, where we tested all different types of air purification technologies, passive, active, carbon, and we really saw some very good benefits. And so I'll show you some of that. Filter capture mechanisms for HEPAs, basically large particles, 10 microns in size, straining, inertial impaction are very important. 0.3 to 10 microns, interception becomes very important, right? The airflow changes direction around a fiber, but the particle's momentum carries it into the fiber. And for very small particles, 0.1 microns and smaller, diffusion, bombardment of the particles with air molecules becomes the dominant force. So this was an earlier graph. We put this together back in 2005 timeframe. And it was just to take a look at how does the filtration on airplanes compare to other environments, into trains, buses, buildings, hospitals. And what I've gathered from listening to Bill yesterday and other discussions is the buildings, you guys have really made really good progress in moving these up. I think you're moving towards the MERV 13. This was the 94% efficient filter. And as you can see, from a particle removal standpoint, we do get a penetration in the 0.1 to 0.2 microns. We've since now gone to the MERV 17, the true HEPA filters. So on aircraft today, whether it's Airbus or whether it's Boeing, we use the true HEPA filters in the recirc system. Very effective, provide essentially particle-free air through the recirc system. Spread of disease on aircraft, definitely a hot topic, I know for you guys as well. It definitely has been for Boeing and the industry. So the industry was hit really hard. When COVID first struck, that first year was really brutal. International travel dropped about 75%. Domestic travel dropped about 50%. 2021, we still had about 30% of the world's population fly, about 2.2 billion. But that was still about 50% lower than our previous years of travel. So real big impact. Spread of disease has been documented on aircraft, but not very much. And so there is studies that show spread of SARS-CoV-1, COVID-2, tuberculosis. CDC put out a study. There was a famous study where disease spread across the aircraft, but when you look at the details of it, it was Alaskan Airlines airplane on the ground, 3 hours with the ECS system off. And so if you sit in a tube and you have the ECS system off, and somebody's sick, you can spread disease. So Harvard themselves, to help the aviation industry, they formed an aviation public health initiative. They looked through all the data on spread of disease. And again, they found that they weren't seeing a whole lot. For flying 2 to 3 billion people a year, you would expect to see a fairly high prevalence if it exists. And they didn't see it. So why? So I'm talking a little bit of science. This is from a Department of Defense. They want to use commercial aircraft to fly military personnel. And they wanted to be sure that the military people didn't get sick. So if somebody was on the airplane that was ill, how did that propagate? How did it spread if there was a spread of disease? And so they did 8 days of studies, 4 on the ground, 4 in flight. They used a 777 aircraft, 767 aircraft with United Airlines, and they released particles, 180 million at a time, and looked at how that spread in the aircraft from right next to the source to several seat rows in front and seat rows behind. And it was really fascinating. They looked at breathing scenarios, they looked at cough scenarios. And so this is some of the actual test equipment and test setup. The mannequin could simulate a breathing, it could simulate a cough. They used IBAC sensors placed in the same seat rows, but also forward and back of the index case. Each release had 180 million fluorescent tracer particles that were released, so a very large plume of about 1 to 3 micron sized particles that were released. They did TAG tracer to look at surface areas as well. And so I'll show you some of the results. They tested in the economy section. So the green, if you can see it, is the mannequin, basically the index case, the 300 million, 180 million particle release. They moved it to the forward part of economy, the business class, and then first class as well. Here's some results. So let's take a look at this middle graph here. This is the 767. And again, releasing 180 million particles, you get a spike and you get a decay. But the decay occurs very, very fast, within 5 to 6 minutes. They took the same equipment to a home, typical home, 1 air change an hour. Same equipment, same release, and you can look at the decay. And then they superimposed it, and then they looked at the exposure. So what would be your exposure if this occurred in a home or if it occurred in an airplane? And you can do this also for buildings. And the exposure is actually 10 times higher in a home. If somebody sneezes in your home, it's going to take much longer for that contaminant to clear the air. And the chance of breathing the contaminant, even after they've left the room, is much higher in a home or office than it would be on an airplane. So this is some of the key findings as well. Again, you can see the index case here, 100%, 180 million particle released. And then these percentages is the percentage of the particles that penetrate the breathing space of that IBAC sensors. And what they found out was that 99.7% of the particles, even in the adjacent seats from the release, do not penetrate into the personal breathing space. Only about 0.3%. And that was out of all the studies, that was the worst case. So what the airplane showed was to have an equivalent of about 7 feet. So if you're sitting next to somebody, it's about equivalent from a concentration standpoint of being about 7 feet away in a building environment. A little bit more of the data. What they also looked at was coughing. I can't quite see it from here, but they have coughing and with masks, without masks. Very low without masks, even lower with a mask. So still a good thing to do, but it drives 0.3% penetration to 0.03% penetration. Kind of their conclusions that they had of their study was that the air dilution, the air exchange rates really play a part on clearing the air on airplanes. If you look at, single homes, you're looking at 2 to 6 air changes an hour. Standard hospital operating rooms, about 12. You get down to about 99.9% removal, about 35 minutes. Aircraft were about 6 minutes for 99.9% removal of the contaminants. So just to kind of summarize why. Airplanes have some unique features that are designed in. We do have very high air exchange rates. We need to do that in order to maintain a comfortable cabin environment. Again, it's very, very cold in flight. We have to exchange that air very frequently, but there's a real benefit for that from a spread of disease. The fact that the airflow comes from the ceiling to the floor has a continuous push of particles in the downward direction. That's another real benefit. The effectiveness of filtration, MERV 17, is a good thing for airplanes. And we've also seen from a lot of our modeling is just the seat configuration. The fact that you're facing forward, there's a seat in front of you, it tends to channel, it minimizes the airflow in the fore and aft direction. We balance the airplane for that, but it also tends to channel that cough or a sneeze within that local area and then out. So we don't see a lot of penetration across multiple rows. And so I hope that kind of answers the why down here. Harvard's review, very low number of infections in travel. Now we understand why. So as an industry, again, we were hit really, really hard. I mean, 75% drop in ridership. Without government help, some of the airlines I don't think would have made it. But to try to minimize the concern and try to add confidence to the travel experience, the entire industry came together and put together kind of a multi-layered approach called the Confident Travel Initiative. Included physical distancing. My flight over, I think this is already going away. I didn't see that so much. Masks. I think masks are going to be required probably until we see how COVID changes, the next evolution of it, if that's going to be a real concern or not. I think the concern is once they remove masks from airplanes or buses or trains, people aren't going to want to go back and start to put them back on. So I think variants are going to be really important to watch. Vaccination, what people can do themselves. And right now, the airlines are still cleaning the airplanes. The airplane lands, they get in, they clean the touch surfaces. I think we understand that COVID is spread more by air than surfaces. But again, what can the airlines do? What all can they do to basically minimize? And so on the longer flights, they do deep cleaning as well.
Are your air filtration personnel NAFA certified? Ask if they belong to NAFA and have their certified air filter specialist or NAFA certified technician designations. The CAFS and NCT designations are earned after rigorous exams and demonstrate that the air filtration professional has a high degree of knowledge and professionalism. To learn more about NAFA certifications, visit nafahq.org.
All right, my last section I was going to talk about is air purification and where I think regulations are going for airplanes. But before we talk air purification, I'd like to talk a little bit about when you fly, what are the major health symptoms that people experience? So this was, I think, still the largest study to come out of ASHRAE. It was done on aircraft. I used to chair this committee when this project was put together way back in the early 2000s. Carried out by Battelle and the FAA Centers of Excellence for Aircraft Cabin Environmental Research. And what their questionnaire showed is for passengers, what are the most prevalent symptoms that passengers experience when they fly? When we fly, what do we experience? Dryness, dry eyes, nasal stuffiness, some seat-related symptoms, some pressure-related symptoms, throat-related symptoms. Cabin crew, similar, but a higher intensity. Also, especially on the shorter range flights, some pressure issues, nasal stuffiness, back soreness, and such. Now, have these symptoms changed much over time? They really haven't. There was a study done by Cathay Pacific on flight attendants. This was a 5-point questionnaire for those who like that type, look at questionnaire research. But if you look at their symptoms, they're really very similar. Dry, stuffy nose, itchy eyes, sore throat, irritated skin. This was a big study we did with American Airlines where a questionnaire was handed out for 3 months across their fleet. And we wanted to understand what are the factors that affect comfort? What are the health symptoms reported by passengers? The longer the flight, the more intensity of symptoms. Downward is worse. But again, you see very much the same type of symptoms being reported. The question is why? We didn't understand why. So there was a big effort pulling together our human factors, our medical universities to really start to understand the why. And what we learned from looking at all the different types of symptoms that could be reported, whether they're cabin environmental or work-related if you're a flight attendant, or individual factors we have ourselves. Of the primary symptoms we see, it's most likely volatile organic compounds and humidity. What can we do about it? So we went to the Technical University of Denmark. They're a leading institution for human subject research on air quality. And we did several years of research with them. And what we learned, I thought, was really quite fascinating. It's kind of all tied into this graph right here, that at very high outside airflow, say 20 CFM per person or more, your humidity is very dry. This is symptom intensity on this graph here. Upward is more symptoms. But symptoms due to humidity are more, right? It's drier. It's 1% humidity we're bringing into the airplane cabin at high outside airflow. Gaseous contaminants are held low, but as we drop in outside airflow, what happens? Symptoms due to humidity get better. Humidity goes up, but so do gaseous contaminants. And so what we discovered is if we put in air purification, we can actually raise humidity but lower gaseous contaminants. And that was seen to be a benefit. So I'll show you some results on that. What we didn't still know is what gaseous contaminants? What should we remove? What should we be targeting? We know these general air purification systems that remove a broad spectrum of contaminants do a good job. But maybe a little more specifically, what should we be targeting? And so we went to Rutgers and we did 3 years of research with the professors there. And again, it's one of those things that you go, aha, okay, makes sense. But it didn't not before we did the research. Bioeffluents are really a primary driver. And the reason being is if you look at the amount of airflow per surface area on a typical airplane, because of the very high air exchange rate, the contaminants from the airplane itself are driven down to very low levels. But what do we still have a high density of as people? It's a lot of surface area. We off-gas as people. We wear perfumes, we wear colognes. What I'd like to do now is, so I've gone through some human subject research. There was actual measurements done in flight across the Boeing fleet, across the Airbus fleet. This was done by EASA, they're the regulators in Europe, the FAA Centers of Excellence. So the same people that did the big ASHRAE study, they also took measurements to look at relationships between the human subject response and the measurements themselves. I'm not going to go into that, but I'm just going to focus on, this is the mean and max. These are volatile organic compounds. I don't expect you to be able to see it, but just from a pictorial standpoint, bunch of VOCs measured, the compilation of Boeing and Airbus aircraft here, but they went back and they took measurements only on the 787. It has an electric architecture rather than the traditional bleed system that I showed earlier. It uses electrical compressors. And so this was to look at bleed air quality, so they wanted to look at that. But what they discovered is everywhere it's green, the 787 had lower volatile organic compounds. And so for virtually most of the compounds, aside from some ground ones at London Heathrow, the 787 was simply lower than all the other airplane out there, whether it was Boeing aircraft or Airbus aircraft. This is the full data set. And so you can look at the many pages. Again, everywhere it's green, the 787 was simply better. And that was true, again, on Boeing aircraft as well as Airbus aircraft. For virtually all VOCs and across the spectrum of volatile organics. It was also looked at, okay, what about across studies? So let's look across decades. Let's look across different studies that have been done. So this is the big ASHRAE study. This is Spangler, he's out of Harvard. Big Guan study out of China. This is out of the Netherlands. This is the big EASA study. If you look at a typical marker for VOCs, toluene, A7 is lower. If you look across the summation of hydrocarbons across the studies, the A7 is lower. Why? What's different about that airplane? It has electric architecture, but that really shouldn't affect the VOCs in the cabin. What is unique is it's the only airplane that has air purification system built in as basic. No other airplane has that. There's an opportunity, it seems, for improvement across the board. Regulations, my last section here. The FAA put forward regulations for ventilation years ago, decades ago, and they based it on ASHRAE Standard 62 pre-1981. And I think we saw in the chart yesterday of ASHRAE and how the ventilation changed over time. And they went down to 5 CFM, then back up to 15. But before that, they were at 10 CFM. And that's what the FAA adopted as regulations on airplanes. It's a prescriptive regulation. And I thought this was interesting when Jerry was talking sensors. The goal, it sounds perhaps in buildings, is to try to move from prescriptive more to performance-based. I think the same thing for aircraft. We're looking at doing the same thing. Right now, the only regulation for ventilation is 0.55 pounds per minute. That equates to 10 CFM at 8,000 feet. We'd like to move to performance-based regulations. Account for the airflow coming from overhead, exhausting at the floor. Account for air exchange rates, HEPA filtration, air purification. And then the very latest knowledge on the human subject research. What have we learned on ventilation, contaminants, humidity, and how can technology play a role, I think is very important. All right, so where we would like to move to is smart systems. In order to do that, filtration is going to play a very key role. Filtration of particulate matter, but also filtration of gaseous contaminants as well. And we think by doing so, we can not only improve comfort, we can improve fuel economy, and we can reduce engine emissions, make it a greener airplane as well. That concludes my presentation. All right, thank you.
Thanks for listening to the Talking Air Filtration podcast, a production of the National Air Filtration Association. Clean air matters.